All right, let's talk about Ohm's law. I've mentioned it a couple times now, but let's talk about it. The first thing is I'm just going to give you guys the equation for it. It's very straightforward. It says that the current going through a wire is based off of two things. The greater the voltage, which is basically the electrical potential, how hard the power source of the battery is pushing on the charges, will increase the current. And that makes sense because batteries are kind of like pumps. And if we increase the strength of a pump, the pressure of the water and how fast it would move it's moving would increase. So same idea here. If we give ourselves a stronger battery, we would get a stronger current. And then it decreases based off of the resistance. And again, that totally makes sense. If we make it harder for the charges to get through, then the current's going to decrease because it's being restricted somewhere. So Ohm's law works out pretty simple to be just I equals V over R. You'll see a lot of the time people write it this way for convenience sake, V equals IR. That's definitely the version that I had memorized going into the exam that I took to become a physics teacher, because it is really easy to memorize, divisions. I don't know, doesn't stick in my brain as well. But the I equals V over R is the more useful one because it tells us that current is the dependent variable, not voltage or resistance. We can physically modify voltage and resistance, but current comes out as a dependent variable off of those two factors. So with those things in mind, we can start solving a little bit more of circuits than we've been able to do in the past. I've got this example circuit here and the very first Veer table that I think you're going to see, although our next video will have several more of them. Um, so I'm going to solve this circuit. And what I mean by solving it is I'm going to find the voltage, current, and resistor for every single resistor and for the total, the whole circuit, like what's happening in the entire circuit. And you'll see where Ohm's law comes in and where Kirchhoff's laws come in. Going quickly though, because definitely the focus of this video is Ohm's law, and then I'll do more on Veer tables. I know that the total voltage is 10 volts. I know I have a 2 ohm, a 4 ohm, and a 12 ohm resistor. Now I'm going to combine these two first because they are just in parallel with each other. So that's 1 over 4 plus 1 over 12. That's going to add up to be, let's see, 4 over 12, which when we simplify that down, that becomes 4 ohms plus the 6 ohm. My total, or 2 ohm, makes my total resistance 6 ohms. So now I can do some quick, oh, no, sorry, that's not right. That should be 3 ohms. 3 ohms. So 2 ohms and 3 ohms, that works out to be 5. Okay. That means that my current then, this is where I start using Ohm's law, my current is going to be equal to my voltage over my resistance. So that works out to be 2 ohms. Or 2 amps. It's 2 amps going through my battery, which means it's also 2 amps going through this resistor here because it's in series with my battery, which means it has to have the exact same current. Now that I've done that, I now know 2 points on my Veer table, which means I can find the voltage. I'm going to do that using basically the modified version of Ohm's law. I can multiply my current and my resistance together to get my voltage, which is 4. So I know that this is a 10 ohm resistor. I know that I just lost 4 volts on that part of my circuit. So now I must lose 6 volts in the other two components of my circuit so that it adds up to 10 as I go around. I'm losing 4 there, so I must lose 6 there. That would be 10, or going on the other branch, lose 4 there and lose 6 volts down there. Now that I've done that, I can find current again. This is going to be 6 divided by 4. Oh, that's gross, but oh well. That's going to be 3 halves. And then 6 divided by, did I do that right? Yeah, I think so. And then I would do 6 divided by 12. That would be 1 half. Um, and if we add up the current going through each side, I have half an amp going this way. I have 3 halves of an amp going that way. That adds up to 2, which is what we said the total current had to be. So it does split there at the junction, like Kirchhoff's junction rule says, but it's 2 amps going into the junction, and a total of 2 amps is coming out of the junction, just going 2 different directions. So that's basically how you use Ohm's law and Kirchhoff's laws to solve Veer tables. The last thing that I need to talk about is Ohm's law and ohmic versus non-ohmic resistors. So a big assumption that you'll make almost all of the time is that Ohm's law actually works, that the voltage and resistance are determine the current. But one of the problems that actually comes up, and what an assumption that we make, is that the resistance of a resistor is always the same. That's not actually true. A resistor actually tends to increase in resistance as it heats up, and since current tends to create heat, what will often happen is if you hook up a resistor to a strong power source, it will it'll start generating heat and then creating more and more resistance as we go on. So your typical ohmic resistor, something that perfectly follows Ohm's law, would look something like this on the graph, where you would see that the relationship between voltage and resistance is always linear. But what really happens is that as we increase voltage, the resistance actually increases a little bit more quickly. So you would actually see something like that in what's called a non-ohmic resistor. Non-ohmic, this is ohmic. So you'll make the assumption always that you can use Ohm's law. And actually, I want to be clear, Ohm's law always does work. The current is always V over R. When we're talking about ohmic versus non-ohmic resistors, what we're really talking about is resistors that have resistances, oh man, I say resistance a lot, but have resistances that are changing based off of voltage, and therefore mean that you'd have to somehow remeasure the resistance in order to reuse Ohm's law over and over again. So big idea though, in general, just assume that you can use Ohm's law. But if they specifically ask a question about non-ohmic resistors, you're kind of going to be looking for setting up an experiment that would look for a graph that looks like this, or you might specifically be given some kind of graph, and they'll say, is this resistor ohmic or non-ohmic? Or over what region is this resistor ohmic? And we could say that, over that resistance, the graphs were pretty similar, and so it was fairly ohmic. But then after that, it was behaving in a non-ohmic fashion. So there is Ohm's law. Thank you for watching.